Welcome to another presentation about the Carolina Bays. I have had several requests to provide a detailed description of the methods that I use to measure the Carolina Bays in my videos. This presentation provides a step-by-step guide for fitting ellipses to Carolina Bays. The tools necessary for this task are Google Earth, the LiDAR visualization tool by Michael Davias, and the Python open source software that fits ellipses to a set of points along the perimeter of the feature. The basic tools for studying the Carolina Bays are Google Earth and the LiDAR visualization tool. Links to these tools are given in the description of the video. Google Earth provides a seamless satellite view of the Earth. There are several versions of the program for different platforms and operating systems, but we will select the version for Windows desktop computers and laptops. After selecting the option, you can start to download an executable file. Click the button to accept the conditions of the software and download the program. Open the download folder and install the executable program. The LiDAR visualization tool is available from the Cintos.org website. Michael Davias is renaming the Carolina Bays survey as the Ovoid Basin Survey, effective with a v3.0 release expected in the fourth quarter of 2023. That release will include seamless coverage across the 48 contiguous United States. The change in name is to attach a common landform name for the slightly diverse ovoid features seen when considering the Carolina Bays, High Plains playas, and the rainwater basins of Nebraska. You click on the download button to get a file with extension KMZ that integrates the LiDAR images with Google Earth. This web page has some instructions that will walk you through the use of the visualization tool in Google Earth. After you install Google Earth and open the KMZ file, you need to customize Google Earth by selecting a few options. This image shows the 3D tab of the Options panel of Google Earth. Number 1. The left column shows the KMZ for the LiDAR visualization. By clicking the checkbox, you can enable and disable the LiDAR visualization. Number 2. The decimal degrees option should be selected for the latitude and longitude. This is the format used by the program to fit ellipses to the base. Number 3. The units of measurement should be meters and kilometers. This is standard for scientific work. Forget about miles and feet. Number 4. Check the terrain box on the left column. This makes it possible to see the elevation above sea level at the cursor position. The elevation is shown at number 5 in the bottom of the screen adjacent to the latitude and longitude. At this point, you're ready to use Google Earth with the LiDAR visualization. For a demonstration, I input the latitude and longitude of a ghost Carolina Bay and click the search button. Google Earth zooms to the desired location and we can see the satellite image transition to the LiDAR image. Using the mouse wheel and the mouse buttons, you can zoom and move the display area. Michael Davias has marked the bays that he has cataloged. A ghost bay is a Carolina Bay whose shape can be distinguished in a plowed field by the faint outline of the sandy rims. LiDAR with a vertical exaggeration of 20 times makes the outline of the bay stand out, but for such shallow bays, the colorized topography does not have a sharp transition of colors at the rim. This makes it difficult to locate the perimeter of the bay precisely. The default view of the LiDAR visualization tool identifies the bays with a red dot and overlays them with the bay shape and heading. Clicking on the red dot displays basic information about the bay, including the bay ID, length of the major axis, and the azimuth. The overlays can be removed by unchecking the boxes for the bays. Unchecking the LiDAR box removes the LiDAR overlay, and checking it again restores all the overlays. Python is a high-level general-purpose programming language. It emphasizes code readability with the use of significant indentation. As of October 2022, Python overtook Java and C as the most popular language. The ellipse fitting program is written in Python, so it is necessary to install the Python programming environment to run the program. Download and run the executable Python module. You may need to restart the computer for the changes to take effect. Python is available for several operating systems, but I will be using the version for Windows. Once you install Python, you can run programs from the command prompt. You can access the command prompt by clicking on the Windows Start button, searching for Command Prompt, and then clicking on the Command Prompt app. You can verify that the Python environment has been installed by typing Python -V and pressing Enter. The program should respond by displaying the version number of the Python program. Now we can download the ellipse fitting procedure. GitHub is a code hosting platform for version control and collaboration. It lets programmers at different locations work together on projects. I place the programs to fit ellipses to the Carolina base in GitHub to make it easy for anyone to use them. To get the programs, click on the Code button and then click on the link to download a zip file with the programs, examples, and documentation. I copy the files from the zip file to a new directory called X on my D disk drive. The file cbcoords.txt contains sample latitude and longitude coordinates for the CB ellipse Python program. The driver 2D Python program was derived from the CB ellipse program, so it can handle latitude and longitude coordinates and also coordinates for a two-dimensional image. The ellipse.py program fits ellipses by the least squares method. It was coded by Ben Hamill and Nick Sullivan Molina and placed on GitHub. This program is called by the CB ellipse and the driver 2D programs. You will not call it directly. The PDF included in the package provides instructions for fitting ellipses to Carolina base. To test the programs, change the directory to the location of the programs. The dir command lists the files in the directory. We can then type the command python space driver2d.py to execute the program. A graph with the sample data should appear. Type the command python space cbellipse.py to execute the program that uses geographical coordinates. I would like to thank Eric Brown for helping me test the ellipse fitting program during its development. He used a computer-aided design tool to plot points along the perimeter of the Tulsa Basin. Eric Brown found the Tulsa Basin in March of 2022 using the LiDAR visualization tool. The Tulsa Basin is a prominent elliptical feature whose margins have been carefully sculpted and which has tangential lines carved on the ground coming to a point. The major axis of the Tulsa Basin is oriented toward Saginaw Bay, so it qualifies as an impact basin like the Carolina Bays and the Nebraska rainwater basins. Analysis with the National Oceanic and Atmospheric Administration Solar Calculator revealed that the lines of the Tulsa Basin are aligned like a solar observatory to mark the change of seasons. Although the basin was used as a fish pond and a swimming hole during the 20th century, there is no record that the lines were made in modern times. Archaeologists are now studying the feature to try to determine if it was made by Native Americans. Now that we have checked out the software, we can start plotting points along the perimeter of a bay using Google Earth. In order to select points along the perimeter of a bay, it is best to start with just the LiDAR image without the shape and azimuth overlays. Select the place mark pushpin in Google Earth. Clear the name. Select the shape of the place mark. A round circle works very nicely because you can see through the center. Grab the place mark with the mouse and move it to the position where the flat area of the bay transitions to the rim of the bay. The change in the colorized topography helps to find the perimeter. Copy the decimal latitude without the degree symbol and paste it in a text file followed by a comma. Copy the longitude without the degree symbol and place it after the comma to complete one line of latitude and longitude. Press Enter to start a new line on the text file. And click OK to finalize the place mark position. This procedure is repeated until all the desired points along the perimeter of the bay have been recorded. This task requires patience and determination. Now that we have a text file with the geographical coordinates, we need to override the contents of the file cbcoords.txt, which is used as the input for the CB ellipse Python program. On the command prompt, we type python space cbellipse.py and press Enter. The results are displayed immediately. The Python program displays the length of the major and minor axes and the azimuth of the ellipse. The ellipse image can be saved by clicking on the disk icon. We can also fit ellipses to the Carolina Bays if we have an image with a scale bar obtained by using a snipping tool to capture an image from Google Earth. WebPlotDigitizer is a useful plotting tool that has online and downloadable versions. For this demonstration, I will use the online version of WebPlotDigitizer. We start by loading an image. The plot type is Map with Scale Bar. The next step is to select the beginning and ending point of the scale. We then specify the map scale size and the units. At this point, we're ready to start recording the points along the perimeter of the Carolina Bay by positioning the cursor and clicking the mouse. When all the points are defined, we click the View Data button to display the points captured. We can trim the coordinates to 5 decimal places and copy them to a text file. We add a title to the data and a line with asterisk 2D to indicate that these are coordinates for a two-dimensional image. We transfer the data to the driver2d coords.txt file, and then we run the driver2d Python program. Since the driver2d program can handle geographical coordinates and coordinates for a two-dimensional map, we need to have a line that helps to identify the input with the asterisk 2D code. We can now compare the results of both digitizations. There's a difference in the length of the major axis of 7.9 meters. Anytime that you measure something more than once, you're likely to get slightly different results. This is why it is a good practice to measure multiple times and average the results of the measurements. Although the lengths differ, the width-to-length ratios of the ellipses differ only by about 1 part in 10,000. A possible source of the difference in the length is that the calculation of the east-west distance using geographical coordinates has to be adjusted based on latitude because the distance between the meridians gets smaller as the meridians converge at the poles. Another source of error could be an inaccuracy in marking the endpoints of the scale in the flat map used for the WebPlotDigitizer, but probably the greatest source of error is due to the lack of a sharply defined rim for the Ghost Bay. The description of this video has links to all the resources that you need to fit ellipses to the Carolina Bays by the least squares method. If you have access to computer-aided design tools that can capture geographical coordinates easily, you can avoid the tedious procedure that I illustrated using Google Earth. Thank you for joining me in the investigation of the Carolina Bays and the Younger Dryas Cataclysm. My book about the Carolina Bays is available at Amazon. Please subscribe to my YouTube channel to be notified of future videos about the Carolina Bays and other scientific topics.